Alright, welcome back everyone. My name is Dr. Katrina McGonigal, and I will be doing the next series of lectures looking at statistical tests that we will use for non-parametric or ordinal data as well as nominal data a little bit later on. When we last left off, we were looking at ANOVA, which we could use when we had parametric or continuous data over here on the left side of our diagram. And although tests like the student t-test and ANOVA are among the most powerful inferential statistical methods, they are not applicable for nominal and ordinal data. So fortunately, statisticians have devised inferential statistical techniques that are appropriate for testing the null hypothesis with nominal or ordinal data. And we're going to begin the next set of lectures with looking at what we would use for ordinal or skewed continuous data. And we're going to begin with the Mann-Whitney U-test, which is what we would use if we have two groups of unpaired data. So our objectives for these next set of lectures in general are to appraise if a specific non-parametric statistical test was appropriate for analyzing data provided in a scientific journal. And specific to this lecture, we want to appraise if a Mann-Whitney U statistical test was appropriate for analyzing data provided in a scientific journal. In general, for ordinal data, we use rank tests, which are used for the analysis of ordinal data or interval or ratio data that do not meet the assumptions that we would need for the t-test or ANOVA. And rather than using the values of observations themselves, rank tests involve ranking parametric data from lowest to highest, then calculating an appropriate statistic. And then this number is used to be compared with a statistical table to assess possible statistical significance, much like we did when calculating our T and F statistic for the t-test and ANOVA, and then comparing these test statistics with a critical value from their respective tables. The Mann-Whitney U test involves analysis of ordinal data derived from independent samples, data that exists at discrete levels of magnitude in the distribution, and data that is not grouped into cumulative frequency distribution. So in other words, individual scores or data values are not lumped together into other groups for further analysis. In general, the Mann-Whitney U test can be compared to the t-test. It's the non-parametric analog. It involves a single comparison that is made between two non-paired groups, and these two groups do not need to be of equal size. It can be performed as a one-tailed or a two-tailed test, and it examines whether the distribution of ranked responses between the two compared samples are significantly different. And how it does this is by calculating a U statistic, and this is based on the rank order of all the data points. And I'll be getting into an example a little bit later to highlight this. From this U value, a probability value is derived, and it is important to note that the calculation of the U value varies by size of the sample. Additionally, the presence of ties of rank between the members of the different groups affects the distribution of U, and this can be corrected for. So for an example, you are comparing a new numerical pain reliever with a placebo group in patients with headache. Patients in each group are asked to rate their pain on a scale of 0 to 10, 1 hour after taking the drug or placebo. And their pain scores were as follows. So group 1 are the placebo on the left side of the screen there. Those are the different pain scores. And in group 2 is our miracle drug, and those are the pain scores there. And you can see that there are a different number of scores in each group, which is fine for the Mann-Whitney U test. What we can do next is rank these samples starting from lowest to highest. So for example here, the pain score of 1 gets a rank of 1, 2 gets a rank of 2, 3 gets 3, and so on and so on. We can see that in each group we have a pain score of 6, so this is a tie, and so what we do is we split the rank between the two, so they would get a 6.5 each for the rank. And then we would skip 7 as a rank, so 7 would get 8, 9 would get 10, and 10 would get 11. And then what we do is for each group we sum the ranks. So the sum for group 1 would be 44.5, and the sum of all the ranks for group 2 would be 21.5. So let's use the same strategy that we have used in the past for analyzing the data that's presented. First of all, we want to make sure there are no assumptions that are violated. So in this example here with our placebo and miracle drug, we have independent samples. They exist at discrete levels of magnitude in the distribution, and they are not grouped into cumulative frequency distributions. Next, we want to state the null and alternative hypotheses. The null hypothesis would be that there is no difference in pain scores between the two groups. The alternative would be that there is a difference in pain scores between the two groups. Next, we want to state our alpha, which for this purpose we will use 0.05. We want to calculate the degrees of freedom, which in the case of the Mann-Whitney U test is not applicable, but some of the other statistical tests that we're going to look at, we will be calculating degrees of freedom. And next we want to find the critical U value, and for this we look at a U table. So here's kind of an abbreviated example of a U table, and you want to make sure it's specific to the level of significance. So since our level of significance is 0.05, we want to make sure that we use that. And these are easily found on the internet, but I've provided you with an example here. In this case, we want to look at what the size of the largest sample is. So for our example here, our largest group has a total number of 6 pain scores, so we would go to 6 on the top here, and then our other group has 5 pain scores in it, so we kind of go across here and we get 3 as our critical U value. So we've looked at the table, we found that our critical U value is 3, and so if our calculated U statistic is less than or equal to 3, then we can reject our null hypothesis. So it's important when we look at the different statistical tests that we make note of whether our calculated statistic has to be greater than or less than our critical value to reject a null hypothesis, because it does change depending on the statistical test we use. So next we're going to calculate our U statistic, and there's a number of different online software programs that we can use to do this as well, and I will give you an example of one at the end of this lecture. So looking at this table again, like we did before, we use the sum of the two groups to determine the U statistic. So for our placebo group we had a rank sum of 44.5, and for our miracle drug group we had a rank sum of 21.5. So next we can calculate our group 1 U statistic. So the equation for this is the rank sum minus 1/2 of the number of pain scores in that particular group times the number of pain scores plus 1. So for the case of our placebo group, it would be 44.5 minus 1/2 times 5, because there are 5 pain scores in that group, times 5 plus 1, which is 6, and we get 29.5. For group 2, or our miracle drug group, we would do 21.5 minus 1/2 times 6, because there are 6 pain scores in that group, times 6 plus 1, which is 7, and we get 0.5. So when we compare the two, for the Mann-Whitney U test, we use the smaller U statistic, which in this case would be 0.5. So since the U statistic is less than or equal to the critical U value, which was 3, we can reject the null hypothesis and determine that there is a statistical difference between the two groups. Now we can use an online program that will show us the same thing. Okay, and you can see here that I have already entered the values for each group. So this would be group 1, or our placebo group, all the pain scores. So you're going to enter the pain scores, not the ranks that you've determined for them, because the program will do that for us. And then group 2, or our miracle pain reliever group, we've entered those there. You select your significance level, which is 0.05, and then we'll do a two-tailed test for this. And then we calculate U. Okay, so we're going to look at result 2 here for the U value. We don't need to pay attention to the Z ratio or anything. So here the U value is 0.5, critical value is 3, and so the result is significant at a level of 0.05. And in the next lecture we are going to look at the Wilcoxon signed rank test. So stay tuned for that.